In the last video, we introduced Newton's third law of motion. And at the end, I promised a trick that I call cleverly choosing your free bodies. And what this is about is that while sometimes Newton's third law is a great help, like we saw in the last video where we were taking a look at the forces from between the truck and the crate, for instance, where it can help you define the directions of forces that would otherwise not be intuitive. Sometimes managing the third law of pairs can be a bit of a pain, and what you can do is you can bury the third law of pairs into the detail of the construction of your system. What do I mean by that? Well, this is best shown by doing an example here. So as our working example, I'm going to imagine that we have three crates, masses M1, M2, M3. Let's make this as easy on ourselves as possible. Let's make the surface frictionless. These masses are tied together by ropes. Oops. We'll call the force due to tension in that rope T1. The force due to tension in that rope T2. And we'll say that the whole system is being pulled by a known force due to tension T. This is what's given. Our hand is on the other end of this rope, pulling with a known amount of force. Now let's say what you want to find is the force due to tension in each of these ropes, and since the ropes aren't their ideal physics ropes, or they're massless and they don't stretch, all of these are going to accelerate at the same rate, and so we can also ask what is the acceleration of all of these. So let me copy that because I'll need it again in a bit. There we go. And now let's proceed by doing what I'll call the unclever analysis. And to be fair, if this is the only way you can think to do it, there's nothing unclever about it. Any way that gets you home is fine. I just couldn't come up with a better name for it. So the immediately obvious thing to do would be to say, make each of these free bodies that you're going to analyze. And so I've drawn the force identification diagrams. We're cutting through this rope, so we'll pick up a force due to tension T1. We'll have a normal force acting on it due to the surface here, N1. And we'll have a long-range force of gravity, Fg1. Okay, here I cut through both ropes, so I'll pick up a T1 and a T2. I cut through this floor, so I'll pick up an N2. Long-range force, gravity, Fg2. Same deal here. I cut through rope number 2, so I'll have a T2. I cut through this rope here, so that's T. Cut through the floor, that's N3. Force due to gravity, Fg3. No forces of friction because we turned friction off in the problem. Okay. So then we can just go ahead and draw free body diagrams for each of these. So here we go, N1 up, Fg1 down, and these will cancel by the second law. The only thing we've got happening is to the right where we got force due to tension T1. So in the land of X, we can write this T1 equals M1A, doing Newton's second law here. My second free body will be mass number 2. So now here, again, same deal. I'll have N2 up, Fg2 down. These will cancel by the second law. I'll have a force due to tension T2 to the right and a force due to tension T1 to the left. And those are a third law pair. I know that T2 has to be bigger than T1 because I'm accelerating to the right. So I can again go into the land of x here and say T2 minus T1 equals M2A. And then I can repeat this again for the third one. So I will have N3 up, FG3 down, T2 to the left, and that is a third law pair with T to the right, and then my applied force T to the right, which is known. Then I can go to the land of X and say T minus T2 equals M3A. And this T is known. So if I take a look at it, I now have three equations in three unknowns. I got my unknowns are T1 and T2 and A, and away I go. Now, the way that this one isn't horrible to do, but the way you would probably go ahead and solve this one would be to say take the second of these equations, solve it for T2 to get that's T1 plus M2A. We can stick that into this third one, so we'll have T minus T1 plus M2A equals M3A. And then from here we have that T1 is M1A, so we can put that in to get T minus M1A plus M2A equals M3A. Then we can rearrange it to get T is equal to M1A plus M2A plus M3A. And then finally, we get that A is equal to our applied force, which we know, over M1 plus M2 plus M3. Then once I have that, I can go back and plug into here to get T1, and then I can plug back into there to get T2, and I solve the problem. Since I'm just talking strategy here, I'm not going to grind it out any further, but you can see that the algebra for this is a bit of a chore. So this is where the trick of cleverly choosing your free bodies comes in. So let me put my system back in here. There we go. And so now let's go and do this the clever way. Oops, didn't mean to do that. There we go. So now let's go ahead and do this, what we'll call the clever way. And it's not that, I'm not making a value judgment about people here, but just, you'll see that the math is quicker. And so that's why I call this the clever way. So doing this the clever way, what you can do is realize that if you think about it, when I look at this crate, there are zillions of atoms all interacting with each other. And we don't worry about those forces acting on each other. They are details of the internal construction of the crate. Later, we will rigorously prove, and it will be a consequence of the third law, why we can ignore these forces that are just details of the internal construction. But what it does mean we can do is we can say, maybe make our systems look like this. Here's one of my systems. Here's another system. And there's another system. Now, at first, it looks like you would think that you shouldn't be allowed to do that. But think about it. From the perspective of this rope here, if you were to put a curtain over, put a tarp or something over M1 and M2, I mean, this is just a rope. It just pulls. It doesn't know. All it knows is it's hooked up to this piece right here. It doesn't know how this is all laid out. So we can take M1 and M2 and our massless rope combined as a system. And then I can do this again with the whole thing, M1, M2, M3 combined as an entire system. And it turns out, though, that this is going to be a lot easier to analyze the problem. Because immediately what I can do is I can draw a free body diagram for the combined system, M1 plus M2 plus M3, this line here. Looking at the force identification diagram, you see, okay, we cut through here and we got normal force and gravity. So I can draw a free body diagram for this. I have my normal force up, I have gravity down, and I have tension to the right. So applying Newton's second law in the land of x, since these are just going to cancel in the land of y, I have my only force, T, is equal to the mass of my system. Now here's the tricky bit. My system is M1 plus M2 plus M3. So the mass is M1 plus M2 plus M3A. And I immediately get the acceleration is the tension over M1 plus M2 plus M3. And then I can go and find my T1 and my T2. So if I go to get T1, if I look at my mass number 1, rope, just T1 is the only rope pulling on it, right? So that'll be T1 to the right, normal force, gravity, which we don't really care about. Newton's second law in the land of x immediately says T1 is equal to M1A, but I just found A here. And then for my system, which is M1 and M2 put together, the only rope pulling on the combined system is this rope here. So for the system of M1 plus M2, the free body diagram looks like T2, normal force up, gravity down. In the land of x, we'll have T2, my only force in x. Now, the combined mass of the system is M1 plus M2 times A. I found A from before, so I can immediately plug and get the tension. So this saved us a bunch of tedious algebra. To be abundantly clear, neither way is more right or more wrong. Whichever way works for you and makes sense to you is the right way to do the problem for you. But this is a trick that allows us to do these kinds of problems faster. So let me do another example here, and I will only do this with the quote-unquote clever approach. So let's imagine that I've got a frictionless surface here. And I've got a M1 equals 8 kilogram block that I am pushing. That's supposed to be my hand. That I'm pushing on the block with. So that's a normal force of my push. And I'm going to want to know how hard I'm going to push. And I have a smaller block right here, mass of 2 kilograms. We'll call it M2. And there is friction here. So our coefficient of static friction is 0.5, just to make the numbers nice and easy. So I want to know is what is the minimum value? That I would need to push this block with to keep this block from sliding down. Now, when you see things like this where there's friction involved and you're asked what is a minimum or what is a maximum, that is code that in this particular instance, the force of static friction is equal to its maximum amount. So we can conclude here that between these surfaces, that the force of static friction is equal to Fs max. All right. So my choices of free bodies here, I will make this, the small block, the red system, and the combined pair O blocks, the blue system. And the strategy here is that with the red system, I can go ahead and identify my forces. I have a normal force from block 1, and I also have a force of static friction acting on it, long range force of gravity acting on it as well. So 1 on 2 there. Now, if I had made the 8 kilogram block my system, I would then also have to account for a normal force of 2 on 1 and deal with the fact that they are a third law pair. And I invite you to do the analysis that way to see that you get the same result. But we go ahead and look here. So we'll have a normal force of due to the table. For the blue system, what we have are a normal force due to the table, no friction because we turned it off, a normal force due to the push, and a long range force of gravity acting on both masses 1 and 2, because remember, this is a combined system. All right, so now I can draw free body diagrams for both of these. So what I've got here is there we go. Force Fs, force of static friction here, acting up. Force of gravity here, acting down. We'll call that Fg2. And then we have our normal force of 1 on 2, acting to the right. All right. So when I go and look at this, in the land of Y, I have the force of static friction acting up. I have Fg2 acting down. That equals M2 A sub Y. A sub Y is 0. Now, from the statement of the problem saying that I'm pushing as little as possible to keep this from sliding, I know that in this case it's Fs max. So I can put that in. So this will be mu static times the normal force of 1 on 2 minus Fg2 equals 0. All right. Now in the land of X, the normal force of 1 on 2 is the only force acting, and that's equal to M2A. So I can take that, put that in there. So I'll have that mu static M2A minus, and I can put in that Fg2 is M2G equals 0. Now, although I don't know the acceleration, I'll be able to plug that into the blue system. So I get that A is going to be equal to G over mu static. So this is how fast the whole thing has to be accelerating in order for the normal force of block 1 on block 2 to be big enough to make the force of static friction be just enough to keep the block from sliding down. Okay, now we can go look at the blue system. The blue system's free body diagram is going to be the normal force from the table. It's going to be the normal force from my push, which I want to find, and is the force of gravity acting on objects 1 and 2 put together. Now here, the only thing we really need to pay attention to is what's happening in the land of X. The normal force of my push is the only force happening in X. The mass of my system is M1 plus M2 combined times A. So I can take the acceleration I found looking at the red system and put that in. So I get that the normal force of my push is equal to m1 plus m2 times g over mu static. And so now we can put in what those are. The big block had a mass of 8 kilograms. The little block had a mass of 2 kilograms, 10 kilograms. How convenient for the math. G is 9.8 newtons per kilogram, so we're up to 98. Divide that by 0.5 is the same difference as timesing by 2. So you need to push with 196 newtons minimum in order to keep it from sliding. You can push harder, but if you do, the force of static friction acting on block number 2 won't change. It just won't be at the ragged edge where it's equal to Fs max. Now you could do this by making the one system the 8 kilogram mass, the other system the 2 kilogram mass. And I invite you to do that. And you'll find that although the algebra is more tedious, you will get the same answer. Alrighty. In the last video in this series, we're going to go ahead and take a look at what a lot of textbooks annoyingly call forces that act as if they are third law pairs, and what the heck they mean by that. Catch you over in the next video.